First, thanks to the previous speaker, Slava Kim, for an exceedingly nice presentation. I think this is a very good example on collaboration over borders, and Slava's long-term association with Riga has been very important indeed. I will have a more general talk here, and as you see, my title is about interdisciplinary laser spectroscopy, and what I would like to focus on is the interplay between basic and applied sciences and the resulting industrial impact. When I was young, as a PhD student in Gothenburg at that time, of course, it was rather suspect to work in applications, and above all with industrial applications, if you were a true scientist in basic work. These things have changed quite a lot over time, and yourself, you come to the conclusion that there is a very sound interplay between all these different aspects. And I try myself to foster that quite a bit, and I give a little survey with some illustration on what we are talking about. And you can see that here in my second slide, which is a generic overview over the process of human progress, if you like, as I see it. It all starts with good schools, with teaching. You cannot stress the importance of teaching enough. And I think we should always keep the flag high. In some contexts, my experience from China, for instance, teaching is not kept very high. It's mostly high-impact journals and so on. It's nothing wrong with that. It's excellent with high-impact journals. But, even more important for a university is the teaching, to bring up a new generation of enthusiastic people. And the basic science, of course, is the foundation of it all. And from good basic science comes good applied science. And out of good applied science comes industrial collaborations and possibly spin-off companies. And this all integrated leads to the enhancement of knowledge and improvement of human conditions. It's difficult, of course, to come to the industrial stage and so on, and you need a good innovation system in place, and that's stressed at most of our universities this day to make sure that the research really can bear the fruits. Okay, I at the end will give some examples on small aspects along these lines from my own experience. Well, teaching is important, and I always stress that. And top left, you can see the very last regular lecture I had here at Lund University on my course on atomic and molecular spectroscopy. It seems to be quite a number of enthusiastic people there in the front row. You can see even a book there, yellow and blue. It's probably the third edition of my Springer book. The other pictures I caught from the internet, mostly about teaching at various places in the world. It's important to invest in teaching, and young people must get enthusiastic and carry science and innovation forward. That's the key thing for university and for us all as scientists and university teachers. Okay, so the yellow book you saw in front row is now blue. This is the 5th edition. And from my point of view, the only reasonable positive result from the COVID epidemic was possibly that finally I got the time to finish the 5th edition of this book, which is now coming also in Chinese in the spring in China. I show this just to show how important I see teaching in any subjects, of course, but since we are talking about laser applications and spectroscopy mostly in this conference, this might be a good example. So in basic science, you learn to handle the sharp tools. And normally nothing becomes more difficult than in the basic science. If you master the techniques there and can make things work, many things to work simultaneously, which is the tricky thing when there is a very many different systems which all are complicated and it should all work at the same time. You teach yourself endurance and never give up. This is from an early example of mine where we do stepwise laser excitation to investigate hyperfine structure and fine structure in atoms on a collimated atomic beam. Big systems and so on, bulky and so on, but you learn a lot from these type of things, and you learn a lot of techniques from the laser spectroscopy toolbox, from which you would like to pick forward sharp tools with which you can do a lot of things, also in applications. It might look like this. This is also a very early picture with saturation spectroscopy, an example of the extremely high resolution you can achieve with the modern spectroscopic techniques in utilizing lasers of various kind. And in a long row of development, this led, of course, to the stabilization of lasers into the utmost precise region, which rendered also the Nobel Prize to Professor Ted Hensch and Jan Hall. Janis Alnis, a key person in Riga, was of course working with Ted Hensch in Munich for many years. And that was extremely good schooling in overcoming any types of problems, which is amply demonstrated now in his work back in Riga since many years. So this is an example of the frequency combs and the stabilization using various aspects of laser cooling, laser stabilization, and so on. This sounds to be extremely basic, of course. Do you need such precision? Yes, you certainly do that. And as a spin-off, industrial spin-off of all that work, from the case of Professor Ted Hensch, with strong contributions by Yaldis Alnis from Riga, they developed these small tabletop, extremely stable clocks with utmost precision, making, of course, GPS systems, any type of precision work, satellite navigation, whatever, spacecraft. It all was enabled by this type of technology. To the left, there is the previous technology, typically a factory filled with lasers to go from the radio frequency regime and refer optical frequencies to the radio frequency time standard, which will be replaced, of course, by optical techniques very shortly. This type of precision also led to Bose-Einstein condensation, also a Nobel Prize, and of course enabling very fundamental studies of solid state phenomena, bridging the small world to the macroscopic world, and maybe enabling fantastic electronic devices for the future. Interestingly, Wolfgang Ketteler, one of the laureates of that year, as a postdoc, he worked in combustion diagnostics for a short time, but not many people know that, and did a lot of laser sheet imaging, which was very useful to image the Bose-Einstein condensations. Used exactly the technique he learned from combustion diagnostics to do this type of Nobel laureate imaging of Bose-Einsteins over at MIT several years later. A good example on how things are interrelated in the most unexpected way. As we know, there were a lot of spectroscopy and laser-related Nobel Prizes through the year. It's a very active field And that's encouraging, especially for young people working in this field. The sky is really the limit. And this is just an example on a Jubilee year, actually the one when the Bose-Einstein got the prize from the Stockholm Concert Hall, where most of the living Nobel laureates under the auspices of the Royal Academy of Sciences were on stage, as you can see here, together with the royal family. One of these applications winning the prize was the chip pulse amplification by Gerard Moreau and Donna Strickland, a recent prize. And we heard very nicely applications of this from the talk of Slava just before here, how you can achieve extremely high powers on tabletop systems, making all these things very realistic. Again, what was a huge factory to produce these high peak powers before is now reduced to tabletop systems in normal laboratories, like one floor below myself, where I'm sitting at the physics department in Lund. We have these high power lasers, which, outperform nuclear power plants by many, many orders of magnitude in terms of peak power. This in Lund all started when we already in 1992 got the first worldwide all titanium sapphire-based chip pulse amplification system, which was a starting point here for the very many high-power laser matter interaction activities that we have had since that. And maybe the most important aspect of that was that with this great laser systems, we were able to attract a young lady from Paris, Anne Louillet, to come with her equipment to try that on our brand new worldwide top laser system, 10 hertz and terawatt output power. And these are examples from the early work we did together, my group and her group here in Lund. Anne stayed on here in Lund, as you know, just to illustrate this type of chip pulse amplification before we turn over to Anne's fantastic achievements. Here is the award for Donna Strickland and Gerard Moreau up in Stockholm. And you might say this might be a bit esoteric first. How useful can these things? Well, it can be also extremely useful. Like Moreau himself, he worked a lot with eye refractive surgery. There is a big successful company doing this type of laser ablation and flip making on the cornea and so on, using this type of tabletop high peak power short pulse lasers. Or as shown from an example on the bottom, how you can accelerate protons and electrons by strong fields. Both aspects are pursued very strongly here in Lund. Proton acceleration by Professor Claes-Göran Wahlström and electron acceleration by Dr. Olle Lund. And of course, in the future, this might lead to cancer treatment of tumors using the Bragg peak of almost tabletop proton acceleration systems, or even treatments of cancer patients regarding with electrons of high energy, already demonstrated here in Lund together with the medical researchers by Dr. Olle Lund. So that's the unexpected results. Well, out of this harmonic generation, all these activities worldwide, so many groups working, finally there was the long-expected Nobel Prize for the attosecond physics, which has a lot in parallel, of course, with mode locking and femtosecond pulse generation in the visible. Now you lock instead the equidistant high harmonics in the XUV region or a soft X-ray region. And what was particularly nice was, of course, that our own Anne-Louise, who stayed on in Lund with us, got her very well-deserved part of this prize, based on her early work and also the continuous experiments leading the way up to the attosecond. This is from the ceremony up in Stockholm, both from the ceremony with Anne and from the Nobel lectures in the Aula Magna, Stockholm University, as you can see in the top left. Bottom right is from the dinner up in the City Hall of Stockholm. There were a lot of people were also interviewed, including myself. That was a great pleasure for me personally. Well, and long ago, already in beginning of the 80s, we started a wall here next door to where I'm sitting in a laser spectroscopy laboratory to put signatures of Nobel laureates visiting. The first one was Professor Art Charlow, and we got his name on the wall. And, you know, being in Sweden, of course, we frequently to the major university can get the Nobel laureates come by to give lectures. So we collected quite a few of them. You can see, for instance, there Gerard Moreau making his signature to the wall, where quite a number of people are added. And bottom right, finally, we had our own, and such a joy, fantastic achievements. Here we are all a part of the Lund Laser Center, which is a partner, as we heard already yesterday from Aigar Satvars, in these applications for teaming. The Lund Laser Center is dedicated to team up with Riga, together with our friends in Münster, and we hope that will be successful now in connecting our centers very closely, based on a long-term collaboration already. And the Lund Laser Center, we started in 1995, and now it has developed quite a lot here. And 200 scientists, 25 professors, 100 PhD students, and so on. And we got certain distinctions there in terms being a profile area and so on nationwide in these areas. And interdisciplinarity is the name of the game, making people work together. And you can see different divisions here. Also working together with synchrotron radiation, which is a key aspect here in Lund. Medical applications are important. As you know, we have the synchrotron radiation facility MAX 4 here, just 2 kilometers away from where I'm sitting, and also maybe 3 kilometers away from where I'm sitting, the European Spallation neutron source, which is now closing its completion. And we see this not as competitors, but we integrate together with them, try to work together. That's the name of the game. Instead of fighting each other, which happens politically quite a lot, it's really disastrous at what you see in the world, worldwide. Work together and achieve the goals together for the benefit of all of us. Okay, I'll switch from these more basic things maybe to a few examples of applied laser spectroscopy, which really, I will give examples from my own experience, quite a few areas, and it all emerged from the basic science. In my own career, during my first 10 years, I had no idea that you could use lasers or spectroscopy at all for anything useful, except elucidating the machinery in microcosmos. And that's, of course, good enough, I would say. It's a very good motivation to do the basic research, but it's certainly nothing wrong if out of that there is also spin-off into useful applications. The useful applications which can bring society forward for the benefit of all mankind. I have always systematically tried to avoid anything related to military application. This is a difficult thing to discuss these days, of course, but systematically I had the idea of never touch anything like that. 20 or 25 years ago, I was even in the first page of a major Swedish newspaper saying, Professor Sune Svanberg Lund, the military will never get my research. And I persist on that. We must really use whatever knowledge we have for unifying people. This is a difficult thing to discuss these days. And your brain is crossed by many thoughts, for sure. Okay. I worked with quite a few fields myself here, energy, environment, ecology, agriculture, food safety, and medicine. Oh, quite a number of things. And that seems, too much, of course, and is probably far too much. But the thing is, from my point of view, I'm doing exactly the same thing in all these areas. And I know nothing about the specialities. But the trick is to work together with those people who know everything about the environment, know everything about ecology, agriculture, food safety, biomedicine, and so on. And as long as I understand and can communicate with them and have the sharp tools in my toolbox that I put up on the table and try to apply in a clever way, then this works very well. It's mostly, from my point of view, a question about the size of the optics, the power of the lasers. To the left, environment. Okay, big lasers, big telescopes. To the right, medicine. Small lasers, LED light sources, fiber optics, and so on. The rest is basically the same, thinking the same, data analysis the same, and so on. And this picture is actually from the period of 10 years, finished now 3 years ago or so, when after formal retirements here from Lund, Professor Katarina and I jointly led a group at South China Normal University in Guangzhou, China. So the same group were doing all these things quite successfully. Environmental monitoring, laser radar system, ecology monitoring insects, and so on. Application of laser-induced fluorescence and other techniques in agriculture, monitoring food packages for quality, or many aspects of laser medicine. And I will just flash some examples from Lund and some from China where this can do, and also illustrate some industrial spin-off, which was part of my talk title, as you remember. We started combustion diagnostics 40 years ago. And these are very early pictures, already from the time when I, more than 40 years ago, were at Chalmers University of Technology. We brought these techniques over here to Lund in my move over here many, many years ago. And this has become very successful. This whole project came out of a moral dilemma. We were trying to do laser isotope separation of uranium when Sweden was pushing nuclear energy more than 40 years ago very, very strongly. And maybe you could get these enriched isotopes by laser spectroscopy. Yes, you can do. And we had a program on that, which I abandoned because I got afraid that you could get weapons-grade uranium in a basement laboratory, and too many applications from country names, which I don't want to mention, had to send their government-supported PhD students to my group. I closed the whole thing for moral reasons only and started combustion diagnostics instead. And we transferred that to Lund, and one of my extremely talented students followed to Lund, Professor Marcus Aldén later, and he has led now a division. He's himself just retired, and they produce almost 200 PhDs in laser-based combustion diagnostics here in Lund. Absolutely world leading in the division that he has been very successfully leading all these years. So that's a good example on what comes out of a moral dilemma when you switch your energy research from uranium over to making combustion efficient. Environment is closely related to energy production, of course. Pollution comes from that, and for more than 40 years, I've been working with various aspects of laser radar, other types of environmental monitoring, where the pulse lasers are used, time delay, like in measurements of lifetimes in atomic physics, the thing I worked with for a lifetime. We will have a talk by Professor Henrik Hartmann from Malmö later. I saw he was on the roster here. Together with him and many of his colleagues, we did a lot of work with laser-produced plasmas to measure lifetimes for astronomy and so on. And what we do here is basically the same. We fire a laser pulse and look at delayed backscattered light in the plasmas or from the atoms, because atoms stay up in the excited state for some time before they can reach the detector. In laser radar, they spend some time over town before they return into the telescope. Everything is, of course, exactly the same, but the scale is different. Here we have microseconds delay and so on. So these are just examples on how you can monitor mercury, for instance, or you can monitor volcanic plumes even 5 kilometers overhead. This we pursued quite a lot in China also, building a system over there with very talented students. And a main reason for doing those was a long-term dream of mine to see whether it was true that there was a lot of mercury in the tomb, underground tomb of the terracotta emperor in Xi'an, according to the chronicles. His sarcophagus, 40 meters below the pyramid, should be flooded around by glittering mercury, the elixir of life, according to 2,000 years chronicles. And if that was true, through cracks in the structures during 2,000 years, this highly volatile mercury might come up. And lo and behold, with our system standing there, we were able to see like a plume, a faint distribution of atomic mercury over that. And you see, not too many people study mercury in Xi'an with laser radar. So this paper is not much cited in the open literature. But if you look at the impact score, the new ones they have on impact on the general society, you can find that this paper is among the 2% top of all science produced. But it only has 9 normal citations, since, you know, people don't do this type of research normally, but it had a strong impact. This is also an interesting aspect, how science sometimes influences the general society much more than internally within science. I just take this as an example. I think these type of aspects will have stronger weight in the future in terms of what we are doing. You can also use the laser beams to study agricultural aspects, like we show here in cornfields close to the Yellow River in China. The spectra coming back gives information about the degree of fertilization and so on, the health of the system. Of course, I know nothing about agriculture, although I was born on the countryside, so I know something from that point of view. But of course, here you work together with the world top professors who know everything about these things and publish together with them. These things are bulky, and what becomes realistic is if you can put the whole thing into compact system. And we were quite early out to use drones. These days you hear about drones all the time for applications which are really frightening, really. You can have payloads on them of different kinds, which can be released, as you know, changing warfare completely. We used their ability to carry 1 kilogram instead of a hand grenade to advanced optical systems, fly over trees, over rivers, and do remote monitoring with infinitely lower price than flying with helicopters. As you can see here, this is a multispectral system flying over trees where the point distribution maps out the trees, showing the concentration of chlorophyll in different colors and so on. And of course, even simpler is to use the drones to fly over waters like the Pearl River in Guangzhou, just 300 meters from our lab. We taught the students to become drone pilots, licensed. There are many drone pilots these days for completely different purposes, as we know. But here you can see the water quality in the Pearl River. A lot of different things, from oils to plankton to other aspects, as you fly by here under GPS control, making these maps. You can study things above the water, floating on the water, but it's also possible to do it underwater, as illustrated there in tank experiments in Guangzhou, where we put the laser beam, which is imaged along the beam on an array detector in a spectroscopic mode, and we can see the motion of animals in the water, the fish passing the beam waving their tails, or the shrimps moving their legs, which of course provides some type of information on what's going on in there related to ecology. That brings me into the area of ecology and monitoring flying insects. As you know, in laser radar, normally we can look at pollutants in the atmosphere, even mercury. But of course, it's much easier to look at particles, which give very strong backscattering signals. Yes, they do. And if you can see small particles, it would of course be possible to see big particles. Not many people did that, of course. Very few, as a matter, but we realized this was a good thing to do. And big particles are called insects, providing huge signals. And why should you look at insects? Well, they are very important pollinators. If we don't have the pollinators, there is basically very little to eat, as you know. And we are doing our best to kill them all by pesticides, by the way. We have the deadly disease vectors, malaria, killing hundreds of thousands of people every year in Africa, mostly children. And you have the agricultural pests here. So there is all reasons to look at that. And we started with that very early with conventional laser radar system, basically firing the pulses, hitting the bug, looking for the fluorescence coming back into the detectors, and we catch the echo 80 meters away in different colors, which of course provides some type of spectral fingerprint who is flying over there. Again, of course, you have to work with ecologists who know everything about these things. So these were bulky systems, but moved the way to very compact system, mostly developed by a former student of mine, Mikkel Brydegård, who is now an associate professor here in Lund, with big European Research Council grants, the second one running now, and doing this type of work. Here is joint work in China over the rice fields, where you see this system where you have CW laser beams being observed by array detectors at slant angle, reading out 1,000 times per second, providing range resolution in systems which might cost only $10,000 or so. Infinitely low price compared to what we are used to. This is from some recent work we did here in Lund. over a small lake about 100 kilometers from where I'm sitting now. And monitoring here, each of these little blips you see, that's an insect flying into the beam. The green points you see, every point there is a bug flying, mosquitoes mostly over the lake, and you can get a lot of sociology. You see the size of them, where they are flying as a function of time, and so on, and what areas they like, what areas they avoid, and so on. We use a lot of scattering, of course, backscattering in all these experiments in atmospheric monitoring, but this is a common phenomenon. Of course, a lot of materials like fruits, slice of apple, like pharmaceutical preparations, they all scatter. Medicine, it scatters like mad. And that led us also to combining the high-resolution spectroscopy for gases with the knowledge we acquired in handling scattering and multiple scattering in the GASMAS approach, gas and scattering media absorption, which produced dozens and dozens of papers in many different areas recently. The general idea is that if you send a narrowband laser through such a material like food, bread, or wood, fruits, whatever, you would see the broad solid state distribution with very little structure, but superimposed of them, the needle stitches from the free gas, if you get in there, 10,000 times sharper. And of course, this was always overlooked, because if you look at solid state materials, there is nothing to look at, so you don't have narrowband lasers. But if you take the narrowband lasers, which we use for the atmospheric monitoring, then you see these needle stitches here, and which opens up all these applications and all this industrial spin-off, for instance, in food packaging, where you can non-intrusively, through the cartoon or through this plastic, monitor the gas and the freshness of the material and so on. We worked with that a lot, and I will finish with some industrial application of that. Let me finish otherwise with examples from laser medicine, which from my point of view, again, is exactly the same from the science and spectroscopy point of view. Whether I direct the beam onto water and look at oil fluorescence broadband, or I look into a tree and look for fluorescence from crops, or I put the laser beam onto the skin and look for fluorescence. The spectra are very similar, actually. It's only the size of the optics. So we worked with that for a long time. And this actually was started almost 40 years ago now, also at the time when the combustion field was handed over to the very prominent Marcus Aldén, who was pursuing that onwards. I instead started work in here together with the medical friends, and in particular with Katarina Svanberg. And here are very early examples on how you can image cancer tumors, for instance, basically using exactly the environmental techniques, how you can delineate a brown spot here and use criteria developed together with the medical people for what pixels fulfill a cancer criterion, what does not, and do real-time cancer monitoring and seeing cancer which are not visible to the naked eye. You can also do the treatments, which we worked with for a long time, the first ones with photodynamic therapy, where you really have not just the heat effect, which is normal in laser medicine, but the sophisticated spectroscopy crossed with medical expertise. Also, heart diseases and so on is a field of application which will probably develop quite a lot for the future, although the early work, which is illustrated here, also tested at Mass General Hospital, by the way, from a small spin-off company. There are some complications on this which I could think can be overdone. It's also, like in all areas, a question, if you have something which you think is very nice, you all the time have to look at what is the competition doing. Maybe they have a better idea to do it. So you should not always get stuck in your first idea. But I think this will also be a future way to, under spectroscopic guidance, clean arteries instead of these huge operations with the doctor talking to the patients why the thing is being performed. I give some examples finally on another important aspect to fight antibiotic resistance, which already Fleming pointed out in his Nobel lecture. It's a big problem by the overuse of antibiotics, training bugs, which become resistant by ample use of antibiotics when it should not be used. That's in the area of sinusitis and so on, where we made, non-intrusive measurement through the skull bone to look at the gases inside by gas mask, see the narrowband structures there, or looking behind the eardrum in small children having a lot of this, consuming a lot of antibiotics, making it resistant in many parts of the world, India, China, even the US, and so on. It might be every third person or more have multi-resistant bugs, bacteria, which means basically that soon there is nothing that works when you really need it. People will be dying from trivial diseases because of this. And new antibiotics are very little developed, since the idea of antibiotics is to sell as little as possible to as few people as possible to avoid resistance. New companies think that is a very good business idea. We work a lot also with trying to save prematurely born babies by monitoring the lung function, which is the all critical thing. There is a spin-off company which is almost ready to do 24-hour cot-side monitoring of the babies, maybe 1 kilogram. It's all about lung function. And you don't want to put them in X-ray machines, which is a standard thing to do now, but rather completely non-intrusively monitor the lung lobes and what's going on. And we try now very actively here in Lund to push this forward to larger patients, where of course it's much more tissue to penetrate, weaker signals. And there we had this idea to instead go through the endotracheal tube. A lot of these intensive care patients have this tube anyway. So you can go down and illuminate from inside and put optical stethoscopes on the outside instead to get very much stronger signal than just illuminated from outside going inside. And we hope this could, of course, for the future be used maybe to steer respirator and ventilators, used a lot. We still remember the COVID, all the people laying in the machines there. Maybe many lives could have been saved by optimum setting in real time of the ventilators for these poor people, even adults. So we are pushing that now quite a lot there, starting with porcine lungs and doing model experiments, as you can see here, where we see the signals penetrating, where we have tapered amplifiers, 1 watt output power, but doing exactly the same as before with the narrowband laser monitoring oxygen and water vapor, but now with 100 times more power, and distribute the light to avoid heat over a larger area. So I come to the end, basically, and let me just say here the interplay about this thing. It starts with the teaching. You should have very good education and focus a lot on that to get people knowing the basics, the tools of science. It's nothing wrong to push that into applied science, and it's nothing wrong and even very desirable to have industrial collaboration like the combustion people in Lund with the big companies like Volvo, General Electric, gas turbines, and so on, but also possibly generate spin-off companies here. And that would all lead to the enhancement of knowledge and improvement on human conditions. I'm so sad to see how we now use all our powers inflicted by all these conflicts to take down the support for the suffering people of the world. And we invest in what is seemed to be necessary, of course. I fully understand all these arguments also, but it makes me so utterly sad to see that human beings seem to be unable to be reasonable, really. Here are just some examples on this. This is the Nola Medical, and they are almost close to agreement now to get their system 24-hour monitoring of newborn babies onto the market. Or the Gasporox company with the food monitoring, pharmaceutical tablets, and so on. I think they have 20 employees have sold hundreds and hundreds of systems worldwide in non-intrusive monitoring, coming from basic science and so on. It's interesting also the PhD student who worked a lot with this with me, Märta Levander. She went off into industry, and she is the boss of this company now. Very successful. And by the university board, she was appointed to be the chairperson of the board of the Lund Laser Center, which we discussed before. So this is an industrial lady, extremely successful, now handling the Lund Laser Center with all this extreme basic science in attoseconds and applications and all the kind, which shows very nicely, I would say, the complete seamless transition from the most basic things to the most applied things. This is the SpectraCure company also doing now clinical trials at many places, actually, for treating prostate cancer by photodynamic therapy. That brings me to the end. I would like to thank very much all students and collaborators, including our friends in Riga, who visited here quite a lot. And it was always such a pleasure to visit. I wish also on behalf of Professor Katarina Svanberg that we could have been there, but for the wonderful city of Riga. Wish you very good luck for all the end viewers here, and for especially the students, to take up the challenges and make the world a better place. So thank you very much for your attention.